Welcome everybody. In this video we're going to cover the monad. There's a precursor video to this one where I talk about the monoids and why function composition is very important in functional programming. And that's generally what monads are about, but there's a second side to them as well. So if you haven't watched that video, go ahead and watch it. That will be crucial to understanding why monads are useful and why we want to use them. But to give you a quick summary, essentially we have a big problem. It's comprised of small problems. We build up many objects in object-oriented programming language to build up a system that solves the big problem. In the functional programming world, we build up many little functions. They comprise the system by using function composition in the functional programming world. So that is how we ultimately solve the big problem. Let's quickly go over the Wikipedia definition. We will see what Wikipedia says about monads, and then I will give my explanation. So the first couple of sentences are very vague, so it's basically just an abstraction that allows you to somehow structure your program generically. So anyway, that's a property of a monad, not like a literal definition, because the literal definition is very mathematical and I would not even be able to understand it, although by understanding the properties of the monad, I can explain what it does and what it is because of what it does. So anyway, monads achieve this by providing their own data type, right? So it's a class, a particular type for each type of monad, all right? So we have different types, which represent specific form of computation. Yep, so this data type represents some kind of function, along with two procedures. Okay, so two more functions. One to wrap the value in any basic type within the monad. So the type has some function, and then another function or behavior where it stores a value. So now this type is essentially a container for another value, and plus it does something. And another property of this container type that does something is to compose functions. Okay, so not only is it a container that holds a value that does something, also glues functions together, composes functions together, connects functions together, and specifically functions that output monadic values, so called monadic functions. So essentially, if we take type A, we will output a containerized type A or type B, right? At the end, we get our container, and then we want to chain that containerized output to the next function, which actually accepts just the value inside the container. And that's essentially the gluing or function composition that is being talked about here. So let's proceed to the code. The way that I see monads is this smart function, glue plus container, right? So it glues functions together, but it also holds a value. And the smart bit about this container glue thing is how it treats that value to basically drag it from the result of one function into the next one. And that's the primary gist of the monad. It holds a value, it glues functions together, the value that it holds, it knows how to extract that value from the container to pass it on to the next function that does not accept a container, but rather the type of the value that is contained. So let's dissect this a little bit. So the smart abstraction of the container is some kind of behavior that we want to handle. So if we do some kind of input-output, it can be asynchronous. In C# we would have to use a wait in order to unpack that value. Then handling nulls, we have the question mark. Handling states, we just use state, like whatever. Try catch, right? Exceptions, go to statements on steroids. And then we have flatten, which is basically like select many. But there is basically some kind of behavior there. And we're going to be dissecting specifically the null, the maybe or optional monad, where we will understand why it's useful to do it that way and how we're actually hiding the functionality in our code away from the actual null value by introducing this monad. So we're sort of building a dome around our application with this monad. So let's take a look at this. Next, the glue, the container part. Again, we are wrapping a value as the dome suggests, because the rest of your application is going to know how to handle this maybe monad from start to finish. You are protected from the null value. Some of the monad examples in C#, again, I've just mentioned async await task is a monad. We await to unpack the value. If we, I think, look a little bit earlier in the C# history, I think we had continue with, same as JavaScript, we have the then function. So if we have a promise, we chain those with thens, at the end of which we can still return another promise, which will be awaited automatically. Okay, so that's the important bit about the monad, is that additional behavior. We're not just returning a value from a function, we're actually returning another promise, and on the end, on the second, then you will get the awaited value. So that's the sort of behavior. That's the extraction of the value and dragging it into the next function. Select many, again, it's a monad. And here with me writing out the types, it might be a little bit clearer to see where select many itself on its own is not the monad. It's the list, it's the IEnumerable behind the list and select many together, which forms the monad. So we have a monad list of t. We select many where we pass the function that accepts the regular t, and we get back a list of t. And again, we select many where we do the same thing, and this is essentially the flattening bit. Then wrapping a try-catch function, we unpack the value from if the exception happens, and then logging in state accumulation. Instead of sort of like always unpacking the value, the motion here is more like threading it and accumulating the logs throughout the context which it passes. So then we can go ahead and write it to somewhere. So hopefully you get the gist. We have a container that holds a value, and then we want to chain a bunch of functions. So we grab it from one container and pass the value in the container to the next function, which again returns a container. It does look a little bit cumbersome, however, we'll see how that can be very useful. And please note, as many popular patterns, C# or frameworks generally already implement these for you. So unless you see some kind of use case that hasn't been implemented yet, I mean, this is your chance. This is for what you're trained for, that unprepared situation, right? So anyway, here we have the full value. It can be null, it can be a string. We want to check if it's not null, perform an operation. So this is our function. If it's not null, perform an operation. If it's not null, perform an operation, right? Or return this thing, and then we square it, and then we dump the number. So hopefully you can see how this is bad. And coming back to the point where C# already implements the nullable monads, this is what you get. So in our case, we have the value. This would be the binding or the then function or the continue with or the select many, where the value that we pass into this function is the trim function, right? And then this is again the bind, the then that you pass the substring into that function. And the same thing happens here. So that's if you can look at this statement and realize that this operator is just a function. There's just a function that sits behind it in the end of it all. Although in C# it is more like syntactic sugar. Here we can agree that this form of writing this out is a lot neater and way better. This is a thing that C# gives you. You could be in a situation where C# doesn't give you this. This is where you want to go from a mess to a clean place and have your own implementation. And again, this is the purpose of why you want to know about monads and not just wait for your favorite programming language to implement this for you. Let's go ahead and see through the steps how we can do this. So we can do the obvious thing. We can implement a function, if not null, where we can take a value and we can apply a function to that value. If that value is null, we just return the default, right? So we just skip the function application, okay? And that's essentially what happens here. We have a value. If it's null, we skip the rest of the function's applications. So that's the sort of behavior that we're trying to replicate. Now you can see there are still sort of inline statements. We call the function, we store the result, we then have to pass the result in again and again. If you've ever used LINQ, this is not what you do. You do .where, .select, first or default or to list, etc. You are able to chain the functions. So that's what we want to do. Let's look at this. If we have if not null, we pass the value in there, we apply the function. We then take the resulting value, again we call if not null, we pass the value that is returned from here and we apply a function. This looks ugly. Hopefully you can agree. It's I would say it's not a big of an improvement from this, although I'd still argue that it is. We want to arrive at this place where we have the value and we just put it into the f function, or we say a, then f, then g, then j. So if not null, if not null, if not null, and this wrapping lambda function, these all disappear. We take the a, we bind f, we bind g, and we bind j, and we get the same result, right? So this is what we're aiming for. This is the most convenient programming model here. And this is what happens in Haskell. The then is actually an operator in Haskell, and it looks like this, angle arrow equals. In Haskell and other functional programming languages, you're generally able to override or basically put a custom function behind the operator where the first and second parameter of the function are left and right. So it's a little bit easier to say what this operator will do depending on what types you're going to supply on either side. So for different types of values, this can be a different monad. So again, then is the thing that should be able to check if it's null, do not run the next functions. And that's what we're trying to achieve. We're trying to achieve this programming model. The then function we are going to now refer to as bind. We will sometimes look back on the first example, we'll say it's the select many, it's the continue with, or the then in the task example, so on and so forth, right? So that's the first step. Hopefully we understand we're trying to go from a bad programming model to slightly better to even better, because we can still see repetition here. Let's get it over with, right? The second step, let's improve the programming model. Here we have foo, we still have our null. Instead of having these functions, we are just binding the functions that we want. Here we got the trim. At the end, we are packaging up the value to nil. So let's quickly take a look at this. I have the nil struct where I can just put the value in the constructor. I have the value. If the value isn't null, it has the value. Then we have a couple of extensions where we have the null functions. This is really something that in Haskell is referred to as the return. I don't know exactly what it is in Haskell, but if you look at other explanations of monads, this is essentially the return, where we take a type and we just put it in the container, okay? So this is the container that we've been talking about. It holds the value. This is the smarts. This is how we compose. This is how we transfer the value. So again, we have the container. We compose two functions with this container. When one function ends, we get a container, we take the value and put it into the next function. And this is what you're seeing here. We have a value, we containerize it by using bind because we just have a simple value here. So I do a return here, I containerize B, and then I bind it to the function. Inside bind, this ends up being a containerized value, and then just the value gets extracted, put in here. I get a containerized value at the end here, and then I bind it to the next function. So this works for this programming model where we have the A, and then we just then F, then G, then J. If we want to start with putting A inside F and then on the end of it receiving the boxed up value and then carrying on calling then. So let's see what we're kind of doing here in terms of gluing functions together. So we have function 1, function 2, input A, and we get returned container B. Then we have function 2 where input is B and we return container C. By combining these two functions, we get function 3 where the input is A and output is container C. So we glued these together, and this is really what the bind, the smart transferring of the value, gives us. We have a function 3, we input A, and this is where we have function 1 accepting an A or A.bind and then bind 2. So again, these are the two equivalent forms of writing this out. We do still have the wrapping lambda function. So again, sort of unpacking the bind, this is the smart transfer. This is this bit where does it have a value? If it doesn't, skip triggering the function. This is where we short circuit, again referring to the first example. This is where we short circuit. This is where the monad does its thing. We get a convenient programming model. We avoid the null value. With the monad, we're creating a DOM around our code and we push out the null value, and all our functions can expect to never crash. And again, just re-looking at the Haskell notation, this is the bind operator. Again, this is what equates to the smart transfer, where function 3 will be A, smart transfer into F1, smart transfer into F2, which is equivalent to this bit. And again, as I said, it's possible to implement the functions behind the operators, which looks something like this, where the smart transfer logic is something that you have to implement inside the function when you assign it to this operator. Our operator bind, this is the implementation, that would be the smart transfer here. Okay, now the last bit that is missing from here is the null value, pushing it out, right? At the moment, nothing sort of stops us from taking this trim function, and let's say we take it out and we have a free floating trim function. Let me close this. We want to use this trim function, right? So here we're binding the trim, but let's say we can still put null in there. So what are we trying to do? Essentially, we have to understand where can a null value come into our application. This is where it could be either in the database already, if we do that. This is where somebody could input a value. We're getting a value from somewhere, right? So we're calling an API. A request is being sent to us. We're pulling a message from a queue. We're reading something from the database. We're reading something from the cache. There are all of these places. These are essentially the gateways, right? So this is the entrance to our DOM. This is where you will have to make a decision to return the nothing. You do not let nulls enter your application by having entry points to your application somewhere here as the entrance to the DOM, where you're making an API call, you're making a database call. At this point, you decide, is it null? Is it empty? This is where you convert it to nothing if it is null, and then the rest of your application can rest easy, because nothing is going to spawn a null. And if you need a null value, you avoid using null by using the nothing. So nothing is just an extension of the original nil with the has value overloaded to always point to false, and original nil always points to true, because the original nil can never not have a value, because anytime we are in a place where it's possible to get a null, we check and we always return a nothing, essentially short-circuiting the rest of the logic that it was about to trigger. Again, the extensions don't really change that much. Instead of returning nulls or defaults where we were before, we are just calling into this nothing value right here. That is just a static value. All right, so same as monoids, monads have rules. Let's take a look at them. So we have the left identity, right identity rule, and associativity. So left identity, all that means is that the monad construction doesn't change functional behavior. We have the hello, we bind trim, we get the value, and again, when you implement your own monads, you overload the equality operator, or you give it some kind of custom way to compare the two monads, because these two classes will be compared as references. I'm extracting the value just for the purpose of demonstration, right? The comparison of the values should have a custom implementation here. Putting the value in the original function or boxing up the hello and then binding it to the trim function should yield the same result if it's the same value. Now you might say, what if I put nil here? And this is what we've discussed in the previous situation. You should never be putting nil in there. And if we put nil in there and it throws an exception, this is what your constructor here should do as well. This is going to force you to always put the nothing check where you are able to get a null. And this is generally at a point where input and output happens. So any connection to the outside world, outside of your application, this is what can bring in nulls. As long as you guard from that, you will never be in a situation where you can put a null in your trim or a null in your nil or maybe or option monad. So then, yeah, I don't know if you've noticed, sorry, I didn't really say it, but the boxing, the return changed the name to ret. So if you see this ret and you're like, what is that? That's basically just boxing up the hello into the monad. So here we have the hello monad, basically rewrapping. The value doesn't change the value. So we have the original monad, we have the monad, and we bind a rewrapping function to the monad, and it will just be the same as the original monad, right? These are just the properties of the monad that you can test in order to verify that you do have a monad. And if you do have a monad, it just behaves in a certain way that is expected, and you're just going to use it and it's just going to work. And then associativity, if you watched the monoid video, it's kind of the same, where the order that you bind in doesn't matter. We have hello, we bind a trim function, then we bind the sub function, and we get the value. Here we have hello, where we bind a lambda function, where we have the trim into which we put the value, and then we bind the sub to it, right? So first we bind these two functions. Here we bind them in order. This doesn't matter, all of them are true. These are the rules for the monads. Again, to sort of reiterate and kind of make the picture complete, it is smart function glue, which glues two functions together, and the smartness of the glue is it knows how to grab the value from the container that the glue is and transfer it to the input of the next function. The sole purpose of this is to achieve two things. First, function composition. So this is so we can keep composing functions to solve the big problem and to remain with a good programming model, where we take the thing that can cause trouble, like IO, null, and we go ahead and push that awkwardness out of our application, leaving us with the problem at hand. Thank you very much for watching this video. If you enjoyed it, don't forget to leave a like, subscribe. If you have any questions, make sure to leave them in the comment section. This can be quite a hard topic. If you found any mistakes in this video or you would like to correct me, you're also welcome. Don't forget to check the description. And as always, have a good day.